Another day, another story. In a lab that appears more like a classroom than the gateway to other universes, Zoran Hadzibabic is leading a groundbreaking experiment at the University of Cambridge. Amid linoleum floors, fluorescent lighting, and scribbled equations on a whiteboard, a quest to unravel the mysteries of the multiverse is underway. The idea of a multiverse, where our universe is just one of many, has intrigued physicists for years. Yet this concept lacks empirical evidence. Hadzibabic's experiment aims to change that. By cooling and manipulating potassium atoms to extremely low temperatures, the researchers aim to create tiny bubbles that mimic the primordial quantum processes responsible for spawning new universes. These bubbles may hold the key to understanding past collisions between universes. Matt Johnson, a theoretical physicist, envisions a day when their experiment's findings align with astronomical observations, confirming their predictions. But what exactly is the multiverse they're investigating? It's the inflationary multiverse, distinct from the quantum multiverse. This idea originated in the 1980s when physicists André Linde and Alan Guth proposed that our universe underwent exponential expansion, creating countless bubble universes. These bubble universes might have collided before separating, leaving behind possible marks or scars in our universe. Finding evidence of the multiverse has been a challenging pursuit for cosmologists. The cosmic microwave background, CMB, is a key place to search, as colliding bubble universes could leave circle-shaped scars. In 2011, Matt Johnson and his colleagues identified 4 patches in the CMB compatible with collision imprints. However, uncertainties persisted regarding bubble formation rates and collision probabilities. To refine their predictions, scientists needed a better understanding of the fundamental processes. Enter the world of quantum theory, where the lowest energy state for spacetime is called a vacuum. In the multiverse scenario, there's an inherent energy driving expansion, tied to false vacuum decay, a quantum process. But the details of this process have eluded us. Complex equations in quantum field theory offer some insights, but they require approximations that limit our confidence in the theory. In 2017, physicists in New Zealand and Australia introduced a game-changing concept, linking false vacuum decay to a quantum phase transition in a Bose-Einstein condensate. This discovery opened the door to experimental exploration. The idea intrigued Matt Johnson and his colleagues, leading to a collaboration with experimental physicist Silke Weinfurtner. They embarked on an international effort to study condensate bubbles and gain insights into the multiverse. Hadzibabic's experiment is a 2-dimensional uniform setup, crucial for creating an accurate analog of cosmological false vacuum decay. Using a box trap of laser light, the team aims to observe bubbles forming and interacting. If their results match theoretical predictions, it could help reevaluate unexplained patches in the CMB and offer new avenues for exploration. The experiment may also shed light on the possibility of universes colliding, potentially producing gravitational waves that could be detected by new observatories. Even if this experiment doesn't prove multiverse collisions, it promises to advance our understanding of early universe dynamics. As Zoran Hadzibabic's experiment inches closer to revealing the secrets of the multiverse, the scientific community remains optimistic, for this journey has the potential to rewrite the rules of our universe's origin. Thanks for watching.